So again, identify the axis, draw in and identify a piece of the object, a square of the object. Then find a variable that you could use to identify where that piece is relative to the whole thing. And can you use that to point at every single piece? So I'm going to identify a piece of the object. I'm going to use a variable to point it out that starts from the axis of rotation. And this has what appears to be one-dimensional symmetry. So I think I can point it out by just using a single variable x. Now, I think I can identify all of the pieces by just using x, because I can go from 0 to L over 2 on one side and from 0 to L over 2 on the other side. So I have a choice. Remember, this is a summation. I can just go from 0 to L over 2 and double it, or I can go from negative L over 2 to positive L over 2. Either choice should work. The math should be the same. And yeah, this x is a vector. So if I go to the left side, I'll have to make it negative. And if I go to the right side, I have to make it positive. But remember, there's going to be a square in there because it doesn't really care which side it's on. So after I've identified my piece, my next job is to see if I can find a way of representing the size of the object using the variable that I'm using for pointing it out. And I can say that this piece is dx wide. And I know that that piece has mass dm. So now I need to find a relationship between dm and dx. I'm going to note that this looks like it has linear symmetry. So I think the mass per unit length of the bar is equal to the mass per unit length of the piece. Just applying the concept of density, that the density of a piece has to be the same as the density of the whole thing. This would not be true if it didn't have uniform density. If it didn't have uniform density, they would have to give me this expression, something that would tell me how it changed. But this one has uniform density. Once I have this, my last step is to solve for dm. And I know this is exactly the same as the last one, with some subtle differences. Now I must assemble my integral, starting with I and my basic integral. I'm going to go through and put the things together that represent this integral. R squared represents the perpendicular distance. That's going to be x squared. I will replace dm with something based on the shape of the object. And I am going to integrate from 0 to L over 2 and multiply by 2. You don't have to do it that way. You can get rid of the 2 and put negative L over 2 in there. It's going to give you the same answer. This is just how I've decided to do it. But it would be just fine if you want to do this. I point this out for two reasons. Sometimes it's easier to work with a 0. Right, because we know that if you can put a 0 in, it's going to just knock out that term. So that's why I tend to try and put a 0 in when I can. Sometimes you have to do it this way, especially if a trig function's involved, because of the nature of trig functions. So if you can, I'd encourage you to put a 0 in when you can, because this is straight addition. This is not a problem. So I'm going to continue the math from here. And the first thing I'll do is pull out anything that has nothing to do with x. I'll find the antiderivative of x squared dx. I'll substitute in my limits of integration. And then I'll simplify and collect terms. 2 cubed is 8. 3 times 8 is 24. And now continuing to simplify, cancel out one of the L's and reduce 2 24ths. Any questions? Is this what you're doing? I know I'm going a little fast, but this part may be worth a point, maybe not. This is what matters. Can you assemble the integral? I want to go to another example. The set of steps we're going to use is exactly the same. And the reason I think that is because the definition of moment of inertia is how far away the mass is from the axis of rotation. So if I'm dealing with a ring, isn't every piece of mass the same distance away from the axis of rotation? Right? This piece over here is a distance r away from the center. And this piece over here is also a distance r away from the center. Wouldn't it be that every piece of mass is a distance r away from the center? The moment of inertia of a ring is mr squared for that purpose. I think you can reason it out. I'm not comfortable with that because I'm trying to express form over function. So I want to use something that we could reason out, but then I want to do it the hard way so that you guys see how the process works. Does that make sense? We'll see. Because when we're done with this, you might feel less happy about it all. Step 1, identify the axis of rotation. I've done so. I put a dot there. We're going to be spinning it something like that, about the axis of rotation. Step 2, identify a piece of the ring, a piece of the mass. I'm going to identify a small piece here. The reason I'm drawing it like a little I or a weird H is I'm kind of indicating that it has a little bit of length to it. So I'm kind of trying to say, look, it's this long. This is how big my piece is. Does everybody understand why I'm drawing it like that? I'm defining where it starts and where it ends. And I'm saying that this is my piece of mass. Now, by the way, this is a piece of arc length. So generally, we tend to use S for arc lengths. So I'm going to say ds for a piece of arc length. Now, we have to find a way to identify where that piece is. You have 2 ways in your arsenal. I don't know that you think of it this way, but you do. The first way we've known about for a long time. identify where that piece is using Cartesian coordinates. The piece is located a distance x in this direction and a distance y in this direction. Be careful before you write that down. This is a way to do so. But this thing is a circle. If I do it this way, I need to come up with an expression to define where every piece is. Do you know an expression that would help us define where every piece is? You may or may not. I hope that you do know that x squared plus y squared equals r squared, the radius. But this might be a pretty hard way to tell somebody where every piece is. For example, if I want to know where this particular piece is right now, I would have to map, well, this x1 and y1 to the radius. I'd have to solve this, and I would have a relationship that would say where every single piece is. It can be done, but how am I going to describe how long that piece is using dx and ds? That might be hard. Now, this subtlety about which one to choose is going to sound super ambiguous. So let me just tell you what you do. If the object is squared off, use square direction. So use rectangular. So if your object looks like a rectangle or a trapezoid or something like that, use rectangular. If your object is circular, don't use rectangular coordinates to describe it. It's in the name. You have another way of identifying where that piece is, something that you've learned in your math class at this point. And the other way involves a different coordinate system. So let's use that other way. So instead of having these axes here, I'm going to take one of them away. And I'm going to say that the top here is 0 radians. I think I can point to that piece using an angle and a length. I think I can go, okay, that piece is a distance r away from the center and an angle theta from the top. So I'm going to use r and theta to define where that piece is. Because here, I think it's going to be easy to address the question, can I point to the first piece, every piece, and the last piece? Can you realize that the first piece would be located at 0 radians? This piece is located at theta radians, and the last piece would be located at 2 pi radians. That would take me all the way around the circle. I think that's a lot easier than for every x having to find r squared minus y squared to the 1/2 power, which is what I would have to do if I wanted to define where every piece is here. I just tell it which theta I'm at. I think that's better. You guys follow? Now, I also have to describe the size of this. And I've given you a method to do this, but you don't think of it this way. An arc length. An arc length is radius times when you do an arc length, you multiply the radius times how much of an angle is swept out. I've already told you this when I said that delta x equals delta theta times r. And that's what tells you what an arc length is. So I've indicated it before, but you also probably learned it way back in geometry and then forgot it just as quickly. So our arc length is, what the hell was that? It's basically r times a small change in theta. So r times d theta should give us our arc length. Have you ever used a compass before to draw a circle? Do you guys know what I'm talking about? Really? Some of you have never used a compass before? That makes me sad. I have a whole box of them. I have safety compasses that don't have the really cool spike that can take out somebody's eye. They're the ones that are made for kids not to hurt each other with. Do you guys know the cool ones I'm talking about with the really long spike? Those are the good ones. When I ordered a box of them, they sent me the safety ones because they were worried that you guys would spike each other with them. So I have a whole box of safety compasses. They're kind of lame. Getting back to work here, we have defined ds in terms of things that are related to how we point to the object. We point to the object by going out a distance r and moving over an angle theta. So now we describe ds in terms of that. We can probably begin to assemble our integral. The only thing we haven't done is we haven't come up with a way of dealing with the density of the ring. So can we kind of agree that it'd be m divided by the length of the ring? Because can't we use this as a linear density still, that the ring is very thin, so I just need its length? And do you know what the length of a ring is? Yeah?
2 pi r.
I think it's 2 pi r. How many of you agree that the length of a ring is 2 pi r? Now, hear me out. How do you know? So somebody just told you that? Here's why I think it's better if you guys really understand where your things come from. ds equals r d theta. ds is a piece of length. If I add up the entire piece of length, this would give me the circumference. This is where it comes from. So add up the entire piece of length. This is what calculus does. We're going to start at 0 and go to 2 pi. We're going to add up the entire piece of length. So if I was to do this integral, r is a constant. So I can bring r outside the integral. There's no integrand, so we assume the integrand is 1. But instead of writing 1, I write theta to the 0 power. If I use the polynomial rule, my antiderivative will have to be theta to the 1 power, evaluated from 0 to 2 pi. If I put in my evaluating signs, I get 2 pi minus 0, or 2 pi r. I mean, I know you know the answer, but do you see why it's the answer now? That to me is more important. I want you to have faith that the math does what you expect it to do. So now, yes, we know the mass density of the ring because we proved the length of the ring. Also, what if it wasn't an entire ring? What if it was a section of a ring or a portion, a semicircle? You may know how to do it, but now you have a method to do it. This has to equal dm over ds. But this also then has to equal dm over r d theta. So we'll assemble our integral. Moment of inertia equals the integral of r squared dm. What is the perpendicular distance from our axis of rotation to our piece of mass? Yeah, but just the capital R, right? The whole radius. So I will replace r squared with r squared, but this one represents the radius. I'm going to replace dm with whatever our solution is here. So I'm going to solve it, but I'm going to use the theta version because that's what our pointer is based on. So dm equals m over 2 pi r d theta. Oops. R d theta. No, that's right. It looks like the r's cancel there. So I'll get m over 2 pi d theta. I'm going to substitute that in because I'm assembling my integral. I'm going to set my limits. I'm going to point to the first piece of mass and the last piece of mass. And this has to equal the moment of inertia. All right, so I'll pull out whatever is a constant and doesn't depend on theta. So that'll be m r squared over 2 pi. And I'm going to integrate from 0 to 2 pi d theta. Again, the physics portion ended right here when I assembled the integral. This is just calc. We just did this integral. It works out to be 2 pi. So I can just write this as mr squared over 2 pi times 2 pi. So, canceling out the 2 pi, I get the expected answer, mr squared. Now, I know we're on club schedule, but we've done the bar about its middle, the bar about its end, and the hoop about its center. We really need to do a disc, but you're going to have to buy into some things to really understand the disc. And it's not something that we can buy into in 3 minutes. So what I want to teach you, I can teach you in 1 minute, and that's something that's left. As you can see, finding a moment of inertia is laborious. It takes time. But there is a simplification that helps you. Because for every single object, there's an infinite number of moments of inertia. I mean, we just found that the work to do this one, 1/12 ml squared, and the work to do this one, 1/3 ml squared, is largely the same. But what if you want to do this one, or this one, or this one? For every single axis, it's a whole new integral. It has been shown that there is a formula that once you find one moment of inertia, you can apply it to a bunch of different points on your object. And it's called the parallel axis theorem. This is heavily used on the exam, worth remembering. It says, if you know the moment of inertia about the center of mass, if you know that one, then you can shift to any parallel axis by multiplying by mx squared, where x represents the shift distance. Now understand, this is the parallel axis theorem. You can't convert to a perpendicular axis using this, but you can convert to a parallel axis. Just walk with me here. The center of mass was 1/12 ml squared. If I want to shift it to the end, I would have added m over the shift distance, L over 2 squared. 1/12 ml squared plus m times L squared over 4. I'm going to get common denominators. 1/12 ml squared plus 3/12 ml squared. Uh, 1/12 and 3/12 is 4/12 ml squared.
Please pardon the interruption. Teachers, at this time, could you please release all seniors to the gym for the panoramic picture? Again, teachers, please release all seniors to the gym at this time.
All right. Folks, the parallel axis theorem works for parallel axes.